Welcome to weeks 4 and 5 of Machine Learning with R, which is the one credit portion of Geography 473-673 Spring Semester 2021. In this week's tutorial, we're going to cover random forest modeling, which is a machine learning approach for classification. So I'm going to click on the link here for weeks 4 and 5. And here we go. Random forest modeling is really just a methodology for classification via machine learning. And basically what we're going to be trying to do here is we are going to try and forecast whether or not there is a forest fire on a given day, given environmental conditions. So we are going to be using a data set which holds information based on Algerian forest fires. So we have date, temperature, humidity, wind speed, rain, some weather observations. Then we have some fire weather indices, such as a moisture code, drought code, spread index, buildup index. And these are based on different wind directions, wind speeds. They're actually mostly based on these weather observations. Then we have the class component. And this is our classification class. And it designates whether there's a forest fire or no forest fire. So it's the presence or absence of forest fire. So first things first, we got to prepare the data. So what we're going to do here is we're going to read in, it's just a CSV data. It's called, it's Bayaya forest fires. And it is, remember, this is an Algerian province. It says forested province in Algeria called Bayaya, and it has forest fire data set. So let's go ahead and let's open up R. I'm going to start a fresh session here on my end. And I'm going to clear this out. And here we go, read in the data set. And then we're going to just plot our data set based on the class. So real quick over here, summary of FF data. We turned it into a, here we go, should be class FF data. It's going to be a Tibble data frame, a Tibble table, and a data frame. So it has multiple classes. But the class variable that we're interested in here is this right here. 122, and the different classes, or the different characters of this class are fire versus no fire. So we see that in this data set, we're just about equal. We have just about an equal amount of days where there is actual forest fire and days where there is no forest fire. So the entire idea of this tutorial is we're going to try, and using this data set, we're going to try and predict whether or not there will be a forest fire on a given day. And the way that we'll do that is through classification. So the first thing that I want to do here is I want to gather some of this data. So this is a unique function from the tidyverse package. I'm going to gather the data. So I'm only going to gather day right here through FWI, fire weather index. We're ignoring the class variable. But what we're going to be doing is we're going to plot gathered based on, we're going to fill it based on the class variable. So it's going to get colored based on whether it's fire or no fire. So here's what we look like. And it might be a little bit better to visualize it here on this. And so what we see is that when relative humidity is lower, we have a higher concentration, a higher density of presence of fire. And vice versa, when we have a higher relative humidity, we have a higher prevalence of no fire. And rain is, we basically have all of our rain events. Basically, if there's no rain, there's going to be much higher likelihood of fire. If there is rain, much higher likelihood of no fire. We also notice that there's a higher prevalence of fire in the August month and a higher prevalence of fire when temperatures are higher. So that's all really great. This data set is actually pretty well organized. It's very neat and tidy, and we kind of already have some idea, some clues here as to what the drivers might be behind indicating whether there might be a fire or a no fire based on a given day. However, let's just pretend that we don't necessarily have a whole lot of information. We don't have a clear picture, and let's just show how we would go about dimensionality reduction. So this is a really crucial if we would have a massive data set with tons of variables, and evaluating which ones are actually important can be really difficult. This is where dimensionality reduction comes in. One of the methods for dimensionality reduction is principal component analysis. And again, we don't necessarily need to do this for our data set because it's pretty small. We have an idea of what everything is, but remember, this is a tutorial, so let's just go through how you would do that anyway. So what principal component analysis does is it projects the data to fewer dimensions that are the most important. So these dimensions are principal components, and they're ordered from most explained variance to least explained variance. So basically, we're looking at these combinations across all of these variables up here, and all we're trying to do is find out, okay, what's the common dimension across all of these different variables? And principal component analysis can reveal important features of the data, such as outliers or departures from a multinormal distribution. And basically, what we're going to do here is, because the fire weather indice variables are mostly derived from the weather observations, we're just going to cut those out of the data set. We're going to call that data set cut data. So let's do that first here. So now we just have temperature, rain, relative humidity, wind speed, and class. And notice what happened to class here. So we had to read it in as first we turned the data set class to a factor. What did that do? It added levels to, we had a fire level or a no fire level. And then we turned that factor to a numeric, which led us to 2s and 1s. So 2 is no fire, 1 is fire. Now, what we can do, because we have a numeric matrix right here, we are going to run this function called prcomp, and we're going to extract scores to try and find out these different dimensions. So these are our different dimensions right here. We have principal component 1, 2, 3, and we see that right here, our principal component has a value of 0.54 of temperature, so we can see already that temperature might be an important variable right there because of its high dimensionality with principal component number 1. And what we can do now is we can put this into a separate data frame, and we can add back into this the fire data class. So now if we look at PCA output 2, we see we have all these principal component values for each row of data and whether or not there was fire or no fire on that day. So remember, these are just different dimensions, so we're trying to reduce the amount of dimensions with our data set. We can use this aggregate function to try and calculate the centroids of the principal component 1 and 2. So basically what we're saying here is that we can calculate however many principal components that we want to have, but really we only care about principal component 1 and 2 because these explain the most variance across all of these different variables. So we're only going to we're going to bind C1 and C2 together, and we're going to compare them with groups, which our groups column is fire versus no fire. And we're going to crunch the mean of that. That's going to be our centroid. Now, what we can do is around that centroid, we can calculate a confidence ring. So we're going to use this right here, this function, which basically what we're doing is, this is more of a complicated way to calculate the ellipsoid around the 95th percentile of confidence around a central point, which we calculated in the centroids. So real quick, here's what centroids looks like. Okay, these are the these are basically the centers of the fire group of principal component 1 and no fire centroid for principal component 1 and likewise for principal component 2. Now we copy this over here, and all this function is doing is we are binding together these groups, and what we're doing here is we are calculating an ellipse around that with a 95th percentile. So it's kind of a complicated way because all we're doing here is we're basically crunching the data on how big the ring is for these different principal components. And now that we have these rings, what we can do is we can plot this confidence ring around or with a polygon in ggplot. And then let's also plot the different principal component values. So here we go. This is our dimensions now. So we're now in this eigenvector dimensionality where we have principal component 1, principal component 2, and we see that higher levels of principal component 1 and lower levels of principal component 2 suggest more of a fire group, and vice versa, we have a no fire group right here. So yeah, so this is kind of what principal component analysis looks like. And again, it would be more useful to use this if we had a larger data set with more columns and more variables. So the other type of dimensionality reduction that we might want to do is TSNE. And what this is going to do is it's just going to remove redundant information and only preserve those high impact information within a data set. So the main difference here is that PCA does not retain nonlinear variance, whereas TSNE does. So very similar to PCA, kind of the cousin here. And we can calculate this with the TSNE package. So first and foremost, what we're going to do here is calculate the distribution of our original data set. So if we go all the way up top here, we have all of this distributions. Oops. So the dist function, so I keep saying distributions, is the distance. It's a distance matrix computation. So we have a distance matrix that's calculated and average the distances in eigenvector terms across these different variables. Now what we can do with that is once we have that matrix created, that distance matrix, we can actually crunch the TSNE, convert it to a data frame, add back in the forest fire class, and then color it based on that. So here we go. We have an eigenvector 1, eigenvector 2. Remember, these are similar to a principal component. These are just important dimensions, but we're reducing our dimensions to only preserve their important ones. So we kind of see that no fire is concentrated up here, fire is concentrated down here. We can also scale our different dimensions within this data set, and with a very similar routine up here. And basically, this multi-dimensional scaling is a technique that creates a map to display the relative positions of the number of objects only given the table of distances between them. So it's based on the eigenvalue distance matrix, and it flows similarly to the TSNE, but we're going to just be using this CMD scale for multi-dimensional scaling. So again, follows the same exact format here. So we're going to calculate our distance matrix, or also known as a proximity matrix, and then we'll just plot it up. And we kind of see right here, for these eigenvectors, what we have is no fire concentrated over here, and fire kind of more concentrated over here. So again, these are just different ways that how you would go about reducing dimensions if you had some crazy large data set. But our data set is pretty straightforward, it's well labeled, and we can actually work with this pretty easily. So one thing that might be useful for a classification problem like this, where we want to figure out a presence or absence of forest fire on a given day, given environmental conditions, is random forest modeling. So this is a machine learning method for classification, or it can also be used for regression predictions, but basically it uses decision trees. So decision trees look like this. So if rain is below 0.05, yes, that means that 54% of the time it's going to be a fire. No, 46% of the time it's going to be no fire. So from there, we now have the next decision. Is relative humidity greater than or less than 76? If yes, if it is below 76, then it's 43% of the time it's going to be a fire. 11% of the time it's going to also be a fire. But we're now down here where we're basing things on different situations. So this is a decision tree. If yes, no, yes, go here, no, go there. If yes, no, yes, go here, no, go there. So you're just asking yourself a series of binary questions, and ultimately you get down here where 38% of the time, if rain is below 0.5, relative humidity is lower than 76%, and the temperature is greater than 31 degrees Celsius, 38% of the time you're going to have a fire. Vice versa, rain is above 0.05, temperature is below 36, and rain is greater than 0.15, you're going to have no fire 37% of the time. This is what a decision tree looks like. Now, these are not exact, and what we're going to see here is I'm going to copy the code over now, and we're going to actually make this in R. But what we're going to see, we're going to use our cut data. But what you're going to see in here is that first things first, we're going to need to set a seed. Why are we setting a seed? Because within the R part is a decision tree making package within R. And whenever you have these decision trees, you're going to have some sort of uncertainty. That uncertainty could be a random crunch of numbers at some point within the model that we're going to use an R part model. And that's just part of the play. Why? Because nothing is exact, right? So we're actually crunching some different numbers here. So the R part model might not be exactly what it looks like here because there's distributions that occur within this model. So remember, R is useful because it makes these models kind of a black box. So we're only concerned about the arguments that we have to plug in. We're not necessarily concerned with how the model is working. However, if you are a statistician, you're probably very concerned with how the model is working. However, not all of us can be statisticians and scientists at the same time. That's why it's useful to have a black box like this. We're going to set the seed though, because that way we will get the same exact values here. If we didn't do that, these values would be different. It'd be roughly the same. You might have a 47% and a 53%, but that's because of the random numbers being calculated here. When we set the seed, we're setting a particular seed within R and its correlation to our computer so that the same random numbers are calculated. Most of the time, the seed is random every single time you perform a calculation in R. So if we ever wanted to do R norm and we want 10 random values, that's what it looks like. However, we do it again, 10 random values, right? So all these values are different. However, if we set the seed to 10 and then we perform R norm, the values are the same. So ignore this one, I didn't set the seed again. But if you set the seed before a calculation, the values will be the same. Otherwise, the seed is randomly chosen. So now that we have that explained, what we're going to be doing here is we have our cut data, right, where we only cut out the weather variables. That's the only one we're interested in. And we treat the class as a factor. So now we have fire and no fire. We're going to add levels to that because it is a factor, and we need to define the levels again. And now, based on this class variable of cut data, we're going to create a decision tree based on these two categories, fire or no fire. And there we go. Because we set the seed, everything is the exact same as it is over here. So yeah, it's really cool. It's a nice plotting method for creating a decision tree, whether fire or no fire, given these conditions. Now that we made a decision tree, we really want to create multiple decision trees that essentially has some different seeds that go into it. Why? Because that way we're not creating a completely overfit model that is just overgeneralizes the data. What we want to do is we want to have multiple decision trees based on different random selections of distributional models. To do that, we need to go back to our train data and our test data. However, in this case, instead of performing it and looking at it like a time series like we did in the last tutorial, where we select 2.5 years of data to be our test data set and then half a year to be our train data set, or vice versa, What we're going to be doing now is we're going to create a data partition randomly. So it's random. It's not going to be based on a time series. It's just going to be completely random. So the way that we're going to do that is we're going to use this create data partition. This is from the Caret package. The Caret package is a go-to machine learning package in R. It can do just about everything. And we're going to use this function called create data partition based on the class of cut data. And we're going to use this function to create a train data set and a test data set. So we can already see that what this p equals 0.7 is that 70% of the data is going to the training data set, 30% of the data is going to the test data set, and we randomly chose which indices go to either. So we have indice 1, 3, 5, 6, 11, 14, so on and so forth going into test data, and the other ones going to train data. So that automatically created a partition for us. And now that we have that, we can bring in our old friend, the core plot package, to just crunch a correlation plot across these variables. So we can kind of just get an idea of how these different variables are correlated. So we see that relative humidity has almost an inverse relationship with temperature, which makes sense. And then we also see that class has almost an inverse relationship with temperature. And this is kind of ambiguous. It could be a positive relationship depending on how it's ordered, whether no fire is 1 or fire is 1. But we can just kind of see that based on the size of the circle here, that there is correlation whether positive or negative. We see that wind speed is kind of low. It doesn't matter a whole lot for class. But let's continue on this train and let's figure out, okay, is there any correlation that is highly correlated? So is there anything that's above 70%? So all correlations are less than or equal to 70%. So there's nothing crazy highly correlated. Now we can actually come in here and train our model. So we need to create a bunch of different decision trees for our random forest. That's what this is doing right here. This is what the caret train function is doing. And we're going to be training it to find the class, fire or no fire, of our training data set. The method is rf for random forest. We're going to scale and center the data, the model in the pre-processing. And then we have a little bit of train control. And this is just kind of some arbitrary, some different parameters that can go into this specific model, the number of times that we are crunching these different numbers that are used in these different distributions and whether or not to save predictions. And we're going to set the seed so that we are consistent. Remember, you can set the seed to whatever you want so long as you keep it. So basically we cross-validated and folded multiple times. So the accuracy, what we did here was we used to select the optimal model. So we chose the highest model. We crunched a bunch of different models that we could have used here, and actually 5 to be specific. And what we did was we selected the ones with the highest accuracy. So this is what the output of model RF looks like. Now, there's also a confusion matrix that is spun up with a model, and that is basically we want to confuse our own model based on these different indices to try and figure out itself whether or not it can get the class correct. So we see that when we do that, we have an error of 0.12 and 0.17 for each of these different classes when we're just trying to confuse our own training data set. And now, based on this model output, we can plot, okay, now that you've crunched the model for random forest, which variable is most important? So we can use this var variable importance, crunch that and plot that. So we see that when it comes to predicting whether there's forest fire or no forest fire on any given day, given these environmental conditions, rain is the most important variable. Relative humidity and temperature are still important, but rain is the most important variable. Wind speed is actually pretty much not super important. I can say that for forest fires where wind speed would be very important, would be in the presence of a spreading wildfire. If a wildfire is existing and it's spreading, wind speed does become a factor at that point. But whether it's when it comes to presence or absence, rain is most important. That makes sense why if it rains a lot, it's going to be really hard for it to be dry enough to spark a flame. So we created this model. We've diagnosed which variables are most important to the model. And now we can actually go and test the model. So we're going to use that confusion matrix, only this time we're going to predict using our random forest model on our test data. So we're going to use a new confusion matrix. So we're going to throw this test data into the model. We're going to try and predict it, and what do we want to do? We want to predict the class of the test data. So here we go. We crunch the confusion matrix, and what we see is we're accurate 82% of the time. These are our confidence intervals, and we have a 0.88 sensitivity, 0.77 specificity, and we have our positive class of fire, negative class of no fire. Now that we have our results, we can take these results and save that into a data frame where we say the actual is fire or no fire, and then this is the probability here of fire versus no fire, and then compared to what the actual is right there. Change the name of that as we see fit. And what we're going to be doing is we're going to add a prediction variable right here that is based on if the results of fire are greater than 50% probability, the result of the prediction is fire. And if the results of no fire is greater than 50% probability, then we make the prediction deemed no fire. Otherwise, it's not available. So now we say we want another column that says results are correct, and it's an if-else statement that says if the results of the actual presence or absence of fire equal the presence or absence of the predicted, then we want the true, it's either correct or not correct. So ultimately, our results data frame looks like this. And what we see here is we have no fire, and the prediction was actually fire, and so on and so forth. And I might need to rerun this just because I think that I forgot to run something. Huh. Not so sure why that's not working. I'm going to come back up here and just run the entire model together. Make sure that my seed is set. Ah, okay. I think that I forgot a step up here. I think that I forgot way up here. There we go. Okay. So see, the main problem was back up here. What happened was we had a lowercase n and a lowercase f here, and that did not match the capital N or capital F in the prediction. So it technically was not equal, but we reran it so that everything was correct. Sorry about that. I just forgot to run a line of code in talking, but now we see where our prediction was correct and where it wasn't. So more often than not, we're actually predicting the presence or absence of forest fire correctly. So what we can do with that information is we can plot up the results using ggplot. So we're going to plot prediction and we're going to fill it based on whether it's correct or not. So now we're just making a bar, we're adding a bar geometry to this ggplot instance. So we see where we are correct in this aqua color and versus not correct based on the fire or no fire prediction. So we are correct more often than not. That's awesome. And then let's use a jitter geometry to plot whether or not we are correct in this way. So we have fire up here, no fire down here. So where we are correct, we have these aqua triangles, and where we're wrong, we have this coral colored circle. So did a pretty good job of this, and now we're showing these probabilities here. And yeah, so this is actually pretty cool because what we're able to see here is that when we have a super high probability, we're doing really well, and then it's kind of in between here where we don't have these crazy high probabilities that kind of have more false values. We're not correct. But on the whole, the model is doing pretty good at predicting whether there's a forest fire or not forest fire. So that's random forest modeling, kind of in a quick tutorial. That's how it's working. And this is a very small data set that is very organized, but it still can be used to kind of show how we can use a random forest model to predict whether or not there's a presence or absence of forest fire. And remember, all that a random forest is just a ton of these decision trees. Now, when it comes to trying to create an optimal model, there's a ton of other arguments that you can add to a particular random forest model. So if we actually wanted to plot our original model, we could plot the accuracy versus the randomly selected predictors. And we could see that the higher number of predictors that we select, also up to 4, we get a higher accuracy here. And this is a repeated cross-validation accuracy. So what that means is that we're cross-validating the data set against itself so that we do not cause any problems. And we see that the higher number, the more randomly selected predictors we have here, the better the outcome. However, if we had even more predictors, remember, this is just a small data set. We only have, if we go back to the importance plot, these are our predictors for trying to predict whether or not there's forest fire or not. So we only have 4 predictors, really. However, if we did have a data set that had a ton more predictors, one method we could use is called hyperparameter tuning to try and figure out what exactly, what variables we should have and how they should be constructed. The way that we do that is through what's called hyperparameter tuning. So what we're going to do here is we're going to add a grid of M tries. Now here's what I mean by M tries. See down here, we calculated our original random forest model. We have this M try. It's the model. It's just the model output we tried to crunch the numbers on a bunch of different variations of the model, and this is what we came up with accuracy-wise. And that's the number of selected predictors. Let's say, for example, that we had a lot more predictors, though. What we'd use is we'd add this tune grid. So we're just trying to tune the model. We're ramping up the number of iterations of the model at the time it's repeating, but we're still under random forest. We're still giving it the training data. And now, when we, I need to stop that. Didn't run everything here. And now, whenever this finishes up running, we will plot it, and this is going to be what the output looks like. So we have a number of more model tries. We have all these accuracies here, and we still only have 4 predictors, though. So when we actually plot this, it's going to create these other predictors for us. Why? Because we've made this tuning grid, and what's going to happen is it's going to kind of show that for this hyperparameter tuning, we're doing less, we're not as accurate as we add all these other crazy predictors. So it's kind of just making up predictors as it goes. It can maybe add a correlation of, relative humidity and temperature. It can add a whole bunch of different things in this black box that is the caret train. But ultimately, all we care about is the resulting statistics. And basically, we had one that was most accurate, and this is our tuning grid right here. So there we go. We finally have that. And then if we plot model RF tune man, and this is where we are actually telling it to tune. We're actually manually kind of trying to tune it ourselves, where we're providing this grid with just, a vector of M tries right here. And there we go. So now the other option we have here is to auto-tune it. So now what we're going to do is just going to change some of these arguments up in here. Everything's the same, except for now the search, we're actually telling it to be random, and the tune length is 15. The grid is going to be the same. And now when we crunch these numbers, our accuracy increases a little bit because we're doing a random search across all of these different predictors to try and see if we can enhance and become more accurate. And what we see here, if we come all the way back up, our accuracy was 0.82 for the M try equals 4. And our accuracy down here was actually 0.84 for the auto-tuned model. So again, this might seem a little bit more confusing. It's a little bit more of extra information, but this is something that you can come back to, which would be very useful in the scenario that you have a super large data set that does not have good columns or variables. So random forests can become quickly complex, especially if there's uncertainty in any classification, but we can definitely use random forest modeling to classify the presence or absence of a forest fire given these environmental conditions. So now that we have gone through this together, for the assignment, you're going to perform the exact same analysis, only instead of using Bayaya forest fires CSV, you're going to use City Bell forest fires. It's set up the exact same way, has the exact same variables. It's actually just a different forest within Algeria. And what you're going to do is you're going to proceed with the exact same workflow, just with this other data set. You're going to create the same exact plots, and then you're going to add those plots to a document. Word, Google Doc, or Markdown, whatever works, and upload that file, Word doc, PDF, whatever, to University of Delaware Canvas.